Hello everyone, my name is Dr. Samara White and I'm a pharmacy resident here at Buffalo Psychiatric Center. Today we're going to be talking about vaccines and immunizations. In this video, we'll discuss the process of immunizations, vaccines, and the types of diseases that they protect against, and then we'll talk about some common vaccine myths that are out there. First, we'll go over some important definitions. Pathogens are any type of bacteria, virus, or microorganism that can cause disease. Immunity is protection from an infectious disease. So if someone is immune to a disease, they can be exposed to it without becoming infected. Vaccines are treatments that are used to stimulate the body's immune system against disease in order to gain immunity. Vaccination is the actual act of administering a vaccine into the body to protect against a specific disease. Vaccines are usually administered through injections, but some can be administered by mouth or into the nose. And lastly, we have immunization, which is the process by which a person becomes protected against a disease, most often through vaccination. This term is often used interchangeably with vaccination. So how do our immune systems actually work, and how do vaccines help to support this? Let's watch a quick video that will summarize this for us nicely.
Immunization is the process of becoming immune to or protected against a disease, usually by receiving a vaccine. Vaccines stimulate your immune system to protect you from certain diseases so you won't get sick or get an infection. Normally, the organs and cells of your immune system defend your body from harmful germs, such as bacteria and viruses. Immune cells are constantly circulating through your body. They monitor certain substances on the surfaces of cells called antigens. Healthy cells have different antigens than diseased body cells or foreign invaders in the body. Immune cells usually ignore the antigens on healthy cells. But when immune cells come across antigens on germs, they destroy the germ. Afterward, the immune cell displays the germ's antigen on its surface. This activates other types of immune cells to help get rid of the infection. For example, some activated immune cells recognize the antigen on infected body cells and then destroy them. Other activated immune cells, called plasma cells, make molecules called antibodies. These antibodies travel through your body and lock on only to germs that have its specific antigen. This marks the germ for destruction. Then, other immune cells attack the germs that have these antibodies. Once the infection is gone, some of the immune cells that were exposed to the antigen become memory immune cells. In the future, if the same type of germ infects your body again, the memory immune cells will be ready to destroy it so you don't get sick. This is called natural immunity. In many cases, it will last your whole lifetime. The problem with getting natural immunity from having the disease itself is that some naturally acquired infections can cause serious complications, or may even be deadly. For example, polio can result in permanent paralysis or death. Measles can cause swelling of the brain, resulting in permanent brain damage or death, especially in children under age 5. And whooping cough, also known as pertussis, can cause complications such as pneumonia, slowed or stopped breathing, and death, especially in babies under 1 year of age. While symptoms may not be severe in all people, it's not possible to know who will be affected enough to become very ill or even die. Vaccines can protect you from getting these diseases and their harmful symptoms. Vaccines often contain a small amount of weakened or killed germs, but some contain genetic material, such as RNA or DNA, that provide instructions for your body's own cells to make the germ's antigen. Usually, you receive a vaccine as a shot. Inside your body, The germ particles in the vaccine teach your immune cells to attack these germs. This process doesn't make you sick, but it does cause your body to make memory cells and antibodies for those germs. As a result, if that germ infects your body later in life, your immune system is ready to fight the infection so that you don't get sick.
Now we'll talk more about the different types of vaccines and what they protect against. So we've learned that immunization is the process that the body undergoes in order to learn how to fight off infectious diseases. And this is so we can gain immunity without becoming infected ourselves. The best and safest way to become immunized is by getting vaccines. There are currently 6 different types of vaccines, and we'll go through these one by one in the next couple of slides. Live attenuated vaccines work by introducing an attenuated or weakened version of a live pathogen into the body, and this helps the body learn how to fight the real pathogen. These attenuated pathogens are not strong enough to cause disease, but they do trigger a strong immune response, a similar response as to if the body was fighting the real infection. And because of this, many people may think that getting the vaccine gave them the actual disease, but this is not true. This response is just the body preparing for the real fight if it comes into contact with it in the future. Because these vaccines cause a similar immune response to a real infection, it leaves behind something called memory cells. Memory cells, just like their name, remember the infection that it's going to fight in the future. And because of these memory cells, some vaccines give lifelong protection after just 1 or 2 doses, instead of needing booster shots throughout our lives. Some example live attenuated vaccines are MMR, which fights against measles, mumps, and rubella; varicella, which fights against chickenpox; rotavirus, which fights against a disease seen in children; and finally there's a version of the flu vaccine that is sprayed into the nose instead of being injected. Next up, we have inactivated vaccines. These use an inactivated or dead pathogen in order to help the body learn how to fight disease. People may also think that they got the disease from these vaccines too, since they also trigger an immune response. But just remember, you cannot get the actual disease from the vaccine. The immune response with these vaccines are not as strong as the ones from live attenuated vaccines, and because of this, sometimes these vaccines require extra doses to make sure the body stays protected. We call these extra doses booster shots. Some example inactivated vaccines include injectable flu vaccines, which are the most common type of flu vaccines. The nasal version that we talked about on the last slide is not used much at all. Other examples of inactivated vaccines include polio, rabies, and hepatitis A. Next, we have something called subunit vaccines. Instead of using the whole pathogen, whether dead or weakened, these vaccines just use pieces from the pathogen, usually just a protein or a piece of the outer shell. And since the body can now recognize those pieces, it will now remember how to fight off the real and whole pathogens. Since these vaccines only use parts of the pathogen and none of the pathogen's genetic information, there is no way that these vaccines can replicate or cause disease. But the downside of these vaccines is that they don't produce as strong of an immune response compared to some of the other vaccines, and therefore they don't provide as long-lasting of protection. Some example subunit vaccines are ones that fight against HPV, hepatitis B, shingles, and certain types of pneumonia. Next up are toxoid vaccines. These also use a deactivated version of a pathogen, but instead of teaching the body how to fight against the actual pathogen, it teaches the body how to fight the toxins that these pathogens create. These toxoid vaccines do require booster shots, but much less frequently than others. Some of these you only need to get every 10 years. Here are some pathogens that create toxins. tetanus, pertussis, which is responsible for whooping cough, and diphtheria. Because of the toxins, toxoid vaccines are our best defense against these. Next up is a type of vaccine that is relatively new, or rather, new to the public. They are called mRNA vaccines. These vaccines have been studied for years, but we haven't really had a use for them since the other vaccines work so well against the pathogens that already existed. But now that there's a new virus, COVID-19, these vaccines begin to come into play. mRNA vaccines use the pathogen's genetic information to give our bodies the instructions that they need in order to fight off the pathogens. Our best example vaccine is the Pfizer COVID vaccine. And lastly, we have viral vector vaccines. These use harmless viruses as a delivery system to provide the body with the information that it needs in order to fight off the pathogens. Examples of these vaccines are the Ebola vaccine and 2 other types of COVID vaccines. So those vaccines that we just covered are the ones that we need here in the USA, but there are some other pathogens that are not found here that you might encounter when you're traveling. In order to make sure that you're fully protected before you go on trips, it's generally recommended that these vaccines are done at least a month prior to your trip. Some example types of travel vaccines are ones against cholera, Japanese encephalitis, malaria, typhoid, and yellow fever. As you can see on the right side of the screen, most of these are needed in areas of Asia, Africa, South America, and the Caribbean. As you know, most vaccines are injected, but there are a couple that are not. We've already discussed the nasal version of the flu vaccine, but here's a list of vaccines that can be taken by mouth: adenovirus, cholera, rotavirus, and oral typhoid vaccines. This is a lot of information about vaccines that we just covered, so we'll watch a video to summarize everything up.
The main types of vaccines include live attenuated vaccines, inactivated vaccines, toxoid vaccines, subunit and conjugate vaccines, mRNA vaccines, and viral vector vaccines. Live attenuated vaccines use alive but weakened germs. They're most like a natural infection and provide a strong disease immunity. Examples are the measles, mumps, rubella, chickenpox, and flu nasal spray vaccines. Inactivated vaccines use inactive or killed germs. You may need several doses or booster shots over time. Examples are the hepatitis A, flu, polio, and rabies vaccines. Toxoid vaccines protect against harmful substances made by germs called toxins. They use weakened versions of the toxins called toxoids. You may need booster shots to maintain protection against diseases. Examples are the diphtheria and tetanus parts of the DTaP vaccine. Subunit and conjugate vaccines use only a specific part of a germ. They provide strong immunity to that key part of the germ. These vaccines may also require booster shots. Examples are the pertussis part of the DTaP vaccine and the hepatitis B vaccine. Instead of using germs or toxins, mRNA vaccines contain a special type of RNA called messenger RNA, or mRNA. mRNA instructs your cells to make the germ's antigen, which triggers an immune response. These vaccines do not carry live virus and do not change your DNA. Examples are certain COVID-19 vaccines. Viral vector vaccines may use either DNA or mRNA to provide cells with instructions to make a germ's antigen. The genetic material is wrapped in a different, safe virus to take the instructions into your cells. These vaccines do not change your DNA. Examples are certain COVID-19 vaccines.
How do you create a vaccine to fight a new disease? And why does it take so long? Well, first you have to identify the virus or bacterium that causes the disease. In some cases, the pathogen itself can then be weakened or deactivated and used to make a vaccine. But this isn't always possible. In these cases, the next step is to identify the pathogen's antigens, unique protein or glycoprotein markers which can form the basis of a new vaccine. For some pathogens, these antigens always stay the same. Other pathogens, like the virus that causes flu, can change or mutate their antigens, and so these must be reanalyzed every year. Once you have identified the pathogen or antigens, you need to decide how you are going to use them to build a vaccine. This is called the vaccine platform. There are a lot of options here, like subunit vaccines that only use part of the pathogen. There are also newer or more experimental technologies, like viral vector or nucleic acid-based vaccines. But we'll get to these a bit later. You also need to decide how the vaccine will be administered. By injection into the skin or muscle, orally like the polio vaccine, or through the nose like some flu vaccines. Each of these options could affect the response the vaccine induces. For now, let's say you've decided on the platform and designed the vaccine. Next, it needs to be tested, first in cell cultures and then in animal models. This might include challenge studies, where animals that have been given the vaccine are deliberately exposed to the target disease to see if the vaccine protects them. Further down the line, and if the disease isn't too serious or effective treatments are available, humans might take part in challenge studies too. Once the vaccine candidate is proven safe in animals, you need to prove you can manufacture it to a high enough standard for people and at scale. This is called GMP certification. If the vaccine passes all of these stages, it's time to begin human trials. Normally, these come in 3 phases, and they all have to be passed. First, the vaccine is given to a small group of healthy people to test for adverse reactions. This is called the safety trial. Second, you give the vaccine to hundreds of people to work out what dose is needed to trigger a big enough immune response. Finally, you can trial the vaccine in thousands of people to see how effective it is. This step is often the slowest, and participants are sometimes recruited around the world. Researchers have to wait for participants to come into contact with the pathogen naturally. By tracking how many become infected, they can work out how effective the vaccine is at protecting the group. It can take decades to gather enough data to be sure. But if you do, the vaccine can finally be licensed. There are still problems to overcome, however. Mass producing a vaccine to a high standard can be a difficult job. And once you've cracked production, you still have to deliver the vaccine to where it's needed. And then there's phase 4 monitoring, keeping track of rare adverse reactions that the vaccine might cause even though it's passed the previous trials. This trial process is very safe, but that comes at a cost. It is also very slow. In an emergency, there are ways to speed things up, like reducing the time spent waiting for paperwork to be completed, or running different trial phases at the same time. But steps are never missed out. By working more efficiently, a protective vaccine could be produced in as little as 12 to 18 months, and advances in biotechnology could speed up production pipelines as well. And there are more ways we could speed up production. Let's come back to some of those newer vaccine platforms. Nucleic acid vaccines don't use pathogens or antigens directly. Instead, they deliver the genetic templates for the antigens. These DNA or RNA templates can be delivered directly or in lipid nanoparticles that help them to enter cells and improve their stability after injection. These nanoscale fat droplets encapsulate the RNA or DNA, protecting it as it enters the body. Some lipid nanoparticles can also act as adjuvants, molecular triggers to kickstart the immune response. Once inside the body, these DNA or RNA templates instruct our cells to start making antigens which activate the immune response needed to build immunity. RNA and DNA are much easier and faster to produce in the lab than antigens are. They're also potentially safer than vaccines that contain whole pathogens. That means they could hopefully be used by people with weakened immune systems. But nucleic acid vaccines are still experimental. Another approach is called a viral vector. Viral vector vaccines work by inserting an incomplete segment of genetic material from a pathogen inside a harmless virus that doesn't cause disease. This then acts as a vehicle for the genetic material, delivering it to the right place in the body where it can be translated into proteins, triggering the immune system. The viral vector may even be self-replicating, increasing the amount of vaccine in the body. Viral vector vaccines are also quick to produce. Safe vectors have already been established, and it is relatively easy to insert different target genetic material into these established carriers. And as the genetic material inserted is incomplete, they can't replicate and cause disease, so they're also very safe. But there is only so much the process can be sped along. Effective vaccines can save millions of lives, but before they are used, they have to be proven to be safe and effective. In the future, researchers hope to develop vaccines against non-infectious diseases, like cancers, based on chemical markers called tumour neoantigens. Vaccine technology is developing every day, and it has a bright future, albeit a slow and methodical one.
In this last video, we'll discuss what herd immunity is and why it's important.
It's important to know that vaccines not only protect you, but your community as well. Many diseases that vaccines prevent are spread from person to person. When only a few people in your community are vaccinated, the risk of a disease outbreak is high. But if most people are vaccinated, it's much less likely for a disease to spread. This is called community or herd immunity. Herd immunity is especially important to protect people who can't be vaccinated. This includes people with weakened immune systems, serious allergies, or other health conditions. Vaccines protect you, your family, and your community from diseases that can be dangerous or even deadly.
Like the video said, herd immunity is created when a large percentage of the population is vaccinated against a disease, and this protects people who can't get vaccinated. Without people to infect, pathogens can't survive. That's because if a pathogen tries to infect someone who is vaccinated, the pathogen will not be able to replicate, and so it dies. If enough people are vaccinated, the pathogen will die off completely. For example, smallpox was once a big deal, and it killed about 300 million people in the past, but now it's considered extinct. However, keep in mind that if vaccination rates drop, there's a risk that these diseases can reappear. For example, measles disappeared from the USA in the year 2000, but since then, falling vaccination rates have led to a resurgence of the disease. This is why it's so important for people to get vaccinated. And now we'll talk about some vaccine myths and some other tips that you should know. Are vaccines safe? Yes, they're very safe, even if you experience some side effects. Do vaccines contain toxic and dangerous substances? No. Even though the ingredients may look a little bit intimidating, these substances are already in our bodies, in the food that we eat, and in the environment that we live in. Vaccines contain a very low amount of these chemicals and have been thoroughly tested. Do vaccines contain microchips or tracking software? No. No vaccines have any microchips or tracking software, not even the COVID-19 vaccines. Do vaccines give you the disease that they're supposed to prevent? No. Remember that you cannot get the disease from taking any vaccines. If you feel sick after getting a vaccine, That's just your body learning how to fight off the infection. Do vaccines cause autism? No. This was incorrect information that started over 20 years ago and has since been disproven, but many people still believe it. Is it safe for infants and pregnant people to get vaccinated? Yes. Infants can and should get vaccinated, especially since they come into contact with many pathogens and they have not developed strong immune systems yet. And it's completely safe to get vaccinated during pregnancy. In fact, it's very important to do so in order to protect themselves and their babies. Is natural immunity better than vaccination? No. Although natural immunity may result in stronger immunity to the disease, the risks outweigh the benefits. It's still safer to get vaccinated. Since vaccines are not 100% effective, there's no need to take them, right? False. Even if they're not fully effective, they still help to lessen the severity of the disease. And remember when we talked about herd immunity, it's important to get vaccinated in order to protect those who cannot get vaccinated and to potentially get rid of the disease completely. Next, let's talk about a couple of other things that you should know about vaccines. First, you should know that it takes at least 14 days or 2 weeks for most vaccines to start working. Next, you should know that you can get 2 vaccines on the same day, except for certain travel vaccines, such as cholera and typhoid. And if you get a live vaccine, you can still get 2 vaccines on the same day, but after that, you must wait at least 28 days before you get another live vaccine. And that's because the immune response may affect it. Any other type of vaccines, except for live vaccines, are okay within this time frame. Some other things you should know: if your arm is sore after getting a vaccine, you can move your arm around, you can stretch it, ice it, or take Tylenol. And a tip to avoid getting sore arms before they happen is to relax your arm while you're getting the vaccine. When you flex your arm muscles while getting the vaccine, it can cause more pain after it's done. Let's wrap up by answering a few review questions. Which of the following types of vaccines produce the strongest immune response? A. Inactivated, B. Subunit, C. Live attenuated, or D. Toxoid? The correct answer is C. Live attenuated. Which of the following is true about vaccines? A. It takes about a week for them to work. B. You can get 2 vaccines in one day. C. They are not safe in pregnancy. Or D. You can get the disease from the vaccine. The correct answer is B. You can get 2 vaccines in one day. Which of the following is true regarding vaccines versus natural immunity? A. Natural immunity does not produce as strong of an immune response as vaccines. B. There are more risks with vaccinations. C. Vaccines are not effective. Or D. There are more risks with natural immunity. The correct answer is D. There are more risks with natural immunity. Which of the following is a vaccination specifically for traveling? A. Influenza, B. Meningitis, C. Yellow fever, or D. Rotavirus? The correct answer is C. Yellow fever. Thanks for learning about vaccines with me. I hope you have a great day.